Welcome to system programming class. So today we are going to begin with the unit number 2 assembler. Okay, we have completed unit number 1 and we are going to start with unit number 2. In the previous class, if you remember, we have discussed the program. So we have written the complete program, whatever we have studied earlier, with those instructions, we have completed the program, we have written it completely. So what are the new things you know here? What are the new things we have used here? Things like, say for example, 49 is a variable name. Okay, here you call it as a symbol. So instead of giving the address, so how you have to actually write the program? You have to write it in form of a symbol. So 49 is going to be the, say for example, 49 is your symbol where 49 is the value stored. So this is what we saw. So how do you store a value? F here means full word. 49 is nothing but the constant which you are storing inside that particular symbol. So that's how we have written the program. We have also included some lines like, for example, BCT for looping. Okay, BR for ending the program. Say for example, we are going to say the program is done. You can control can be transferred to execute some other instructions, some other set of instructions can be executed. So that is BR we used. Then we also used BALR, branch and link. We said which is the base register and what is the address you're going to store there. Okay, apart from that there are also sudo ops start using. Okay, and DC and all are the sudo ops we also have in this particular program, right? This is what we discussed in the previous class. The same program can also be rewritten like this. For example, let us say here, so there is L 3 comma is equal to F. What do you mean by that is equal to? There is directly giving us, instead of using symbols like 49, instead of using symbol like 4. Okay, what are we doing is we are using literals, directly placing the literal there. So instead of using a DC command and then naming a variable or naming a symbol as 49 and storing 49 inside that, what I'm saying is I'm not using any symbol here. Directly I'm going to place a literal. So for example, just look at this line. So 49, let us take the same example of 49 only. So this line here you can see 2 comma. Okay, in the previous program which I showed, we had FORTY 9. Okay, instead of giving a symbol directly, a literal also can be used. This is the same program using literals. Only change here is wherever there was a symbol, we are going to replace it with a literal, but you cannot directly write F49. You have to say is equal to F49. That is the syntax, is equal to F49. So similarly is equal to F10 is equal to F4. These are some changes which we have done. Yes, one more change you can see here is BCT. So here BCT in the previous program we have written it like BCT 3 comma loop, if you remember, right? But here we are saying instead of giving loop we are again using a value here. So how is that given here is star minus 16. So what do you mean by star minus 16? Say see the previous screen. So we are now talking about BCT, this one, right? Instead of loop we have used star minus 16. Okay, so what do you mean by star asterisk? Already I have told you, we saw one example for using asterisk comma 15 is what we saw. I told you asterisk is nothing but it is going to point to the current instruction. So address of the current instruction is what asterisk means, right? So what is the address of the current instruction? If in this line if I say asterisk, the address of the current instruction is 24. So there I'm saying asterisk minus 16. So I have to subtract 16 from 24. So 24 minus 16 will give me 8. Okay, so instead of saying loop, what I'm saying here is I'm going to say asterisk, which means current address 24 minus 16. So 24 minus 16 is nothing but 8. So again you're saying the loop value you have to loop to location 8. So that's what you have given here. So this is again another way of writing the same program. Yes, right. So now we will start with what do you mean by an assembler. What do you mean by an assembler? Assembler is used to convert your assembly level language program into machine level language. So what do you mean by assembly level language program, converting them into machine level? So we know that we have literally studied it many times in our course, but what do you actually mean now? Actually, your idea will change. Yes or no? Why? Because so we also have seen how it is done. Say for example, in this example, when we studied the instruction types, you know how if an instruction AR 3 comma 0 is in front of you, you definitely know to write the you know the format, and based on the format you know to write it this way. Yes or no? So you know how to write it this way. So what have we done? We have actually assembled the instruction. So the instruction which we had in a assembly level language form, which is AR3, 4, is now assembled with into zeros and ones. This is what we have done. Similarly, we have another instruction, RX instruction, and then we have assembled it. Okay, so just see this instruction. We have assembled it, but is it that easy assembling? Okay, what are the things you should know before assembling? Right, before assembling, for example, AR3, 4, I have all the information with me. It is just two registers, so I have everything to convert. I know the opcode of AR. I know what is for the first register I'm using, what is second register I'm using. Yes, it is easy. I will be able to do this. But here, so what are we using now in our programs? We are not going to use any address. We are only going to use some symbols, right? So what are the things I should know? I should know things like what is the base register, what is the contents of the base register, what is the index register, what is the contents. So what is this address? 904 is a relative address. What is the absolute address? You should know all that. After that, only you will be able to write these displacements. Okay, this part you will be able to write it only after you know where it is actually placed in the main memory. You understand? This is one challenge we have, right? Similarly, as we go, you will know what are the challenges we have, how are we going to overcome, what methodology we are going to use to assemble an instruction. Okay, assembling an instruction simply means converting it into zeros and ones. Yes, we know how to do it, we have done it also, we know how to do it, but there are some challenges. If we are able to overcome those challenges, then it is going to be very pretty simple to convert your assembly level language program into machine level language, which means to assemble a program. It is easy to assemble a program. Okay, let us see how it is done. First, let us take an example. Okay, so previous program, yeah, we did take an example. That is the program which is going to be a little bit complicated. So I will take a simple program now. We will try to assemble this simple program so you will understand it better, right? This program, the name of this program is John. So you can see the name of the program here is John. So what is this? Start. Okay, we are going to say start 0. I'm going to start here, first location, using asterisk comma 15. Asterisk, what did I tell you? Asterisk is nothing but it's going to store, take the current location, and it's going to, that address is going to be stored in the base register, right? So let us talk about the relative address here. I'm going to say the relative address here for L is 0. Why? Because start and using or sudo ops. Okay, so the actual program begins from this location only, so this is going to be stored in at location 0. Okay, so this is a RX instruction. So next one is going to be 4 and next one is going to be 8. So this is the program we have, right? So load, add and store. So what is this program doing? You will understand this program, I don't have to explain it to you. Load 1 comma 5. So there is a symbol 5. So the contents of this symbol 5 has to be loaded into register 1, has to be loaded into register 1. Add instruction, the contents of what, register 1 has to be added with the contents of the symbol 4, okay, or the variable 4, right? You're going to add register 1 plus variable 4. After adding, the sum is going to be present in register 1 only. So I'm going to store that sum into a variable called temp. Temp is the variable, or your symbol is going to be known as temp. So you're going to load a number from 5 and add that with a number from 4 and store it in a register in a symbol called temp. What is stored in 4 and 5 is the next line. 4. Okay. 4 is nothing but number 4 is stored. 5 is nothing but number 5 is stored. So 4 plus 5 is going to be 9, and that is going to be stored where? In temp. Okay. Just for us to just refresh, DC here is going to be define constant. It will tell you that one full word is required for 4 and the value stored inside 4 is 4. Okay. Similarly 5, one full word, value stored is 5. But temp, we don't know what is the value stored inside because we have to find out. The program itself is for that. So I'm just going to say define storage only. No define constant can be done here because we don't know the contents of it. So we are going to say define storage, one full word, that's it. After we execute the whole program, then the contents of temp will be 9. Yes or no? So that is the, we are just adding two numbers. So we have two numbers, one in symbol 4, one in symbol 5. We are adding that and storing in temp, symbol temp. Right. Now I have to assemble this. Okay, so let us take for example, I'm going to assemble this instruction, say L. I will take L into account. So yes, L opcode of load instruction, you will definitely know the first register we are using is register 1, so you can convert that also into zeros and ones. It's going to be all registers is 4 bits, right? You remember the formatting. So 0001 will be the formatting there. 5 here is nothing but your symbol. Now for you to know 5, you should know what is the address. This address you should know. Now do you know that address? No, we have not even allotted any space there. Okay, we have just had one line. We are using 5. Only later in the program we are going to allot space there. Only then you will know the address. Okay, for you to even allot space for 4, you should first of all know what is the address here. After that you should know what is the address here, then and so on, right? So we only know we have started at 0. Okay, we don't know now at this time, we don't know what is 5, so it is a question mark. We will leave it, we have to leave it. Come to the next line. Yes, it is an RX type of instruction, so it is going to be 4 bytes. Next again, from after 0 it is 4. A same problem here also, we don't know what is the address here. Only we saw that RX instruction, remember, only if you know the what are the things you should know. You should know the base register value, and you should also know the address. So only when you know all these things, you will be able to resolve. Okay, base register value, yes, using will tell you what is the current location. If this program is loaded into the main memory, that location you can add to the base register. That is not a problem. At least you should know what is this address. Okay, if you know the relative address, you can add it with the base register. So we don't know the relative address as of now, right? So this is the problem. So how can we solve this problem? Let us see. Okay, the here the concept says you need 2 passes to do that. First pass, you will read line by line, keep allotting addresses. So once you come to temp, you would have allotted addresses for everything. Okay, again pass 2, when you go again and look into it, now you will know what is the address of 5. So replace 5, 4, temp and all these things with the actual addresses. When you do that, that can only happen during pass 2, because pass 1 we don't know what is the address, so we need one more pass. So again we have to start from the beginning, read line by line. So at pass 2 you will know what is the address of these symbols. Yes, so this is a simple program. This is how we solved it. There could be big complex program, so we should have a method to do it. It should be a standard method which we can follow. So what are we going to do is the next problem. So let us see what happened in pass 1. So I'm going to just tell you this is pass 1 and pass 2 again. So as I told you, we don't know what is this relative address here, so we have left it blank. Again we know it is 4, but we don't know what is the address of 4. We left it blank. We know it is 8. We don't know what is this address, so left it blank. After 8, the next one is, after program is done, you have to store the data. First at location 12, I'm going to store what? 4, right? 4 is going to be stored where? At location 12. So 4 DC, what happens actually? Number 4 is going to be stored in the location 12. Similarly, 5 is going to be stored in the location 16, and at location 20, after executing the program, some value will be stored, but you know the address now. For temp, you know the address, that address is 20. Okay, we just have to fill these things, right? First see, load 1 comma 5. So what is the address of 5? Address of 5 is 16. So I will say load 1 comma 16 of 0 comma 5. Yes, so I have all the components with me. So what are the things I need? I need the base register. I know what is the base register now. 15 is the base register. Yes, so I know what is the index register. So these two things are required for my formatting. I also very badly need what is the relative address or the displacement. Yes, so now will I be able to convert it into zeros and ones using the format? Yes, I will be able to do. So what have we done? We have, now we know how to, now we have come to a stage where I can easily assemble it. I can easily convert it into zeros and ones. Similarly, A1 comma 4, the address of 4 is nothing but 12. So A1 comma 12 of 0 comma 15. This is how we assemble a program. 1 comma 20 for temp. Yes, so this is how you assemble a program. It's a simple program we have taken as an example just to demonstrate what happens during assembly. So this is how, this is the work of the assembler. So read line by line, it has to find out the address of all the symbols. Yes, it has to find the address of whatever is left out here, blank things like symbol 5, 4, temp, it has to find out. So how can we do that? How can you find out the address for all the instruction and for all the data? When it knows the address of all the instruction and data, then it can easily assemble it. Okay, so how are we going to do it? So I told you there is a standard method to do it, right? So what is that standard method is? Here we are going to have a lot of databases. We are going to have 5 databases. Okay, so after you fill the 5 database, you will have a clear cut idea of what is what. You will have all the values in your hand, and then you can easily assemble it, convert it into zeros and ones. So what are the things you require? Okay, so there are these tables. So let me list out the tables. First is MOT, machine op table. Okay, second one is going to be called as POT, pseudo op table. Third one is called as symbol table. The fourth one is going to be called as literal table. Fifth one is the base table, right? I will again tell you: MOT, POT, symbol table, literal table, and base table. Okay, so let us see one by one. What do you mean by MOT? What is MOT? I told you machine ops. So whatever is, all the instructions comes under machine op only. So the list of instructions of IBM 360 is going to come all be present in this particular table that is called the machine op table. All the instructions will be there. See, for example, for starting from the first instruction, there is an instruction called A. And starting from that, you have all the instruction which is going to be stored in this machine op table. Okay, is there any user defined instruction? No, everything is already defined by the system. Okay, so this table is called as a fixed table. So everything is already defined by your IBM 360. So everything is fixed here, so you don't have any user defined value. So this table, one of the table comes under fixed table. So there is also another table in fixed. Let us see that later. Yes, so what is the structure of this particular database? So what is the structure of this database is first opcode. Yes, first and foremost thing, mnemonic opcode. So opcode has to be written. So what is the size it is giving you? So the size it is given for you is, just imagine it to be a database, the table which you create, right? This is going to be the structure of the table. So what you will store? You will be storing opcodes with using with 4 bytes. Okay, 4 bytes will be given for you. You have to store the opcode. So you will store A, and then for all the other bytes you're going to say blank, 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 blank space, right? So why 4? Because the maximum number of instructions, okay, is only going to have 4 characters, so we are going to allot 4 bytes, right? The next one is called as the binary code. What is the binary code? This is nothing but your, this is your instruction, this is your opcode. For example, A, we have seen one example, A. Okay, the opcode of A is 5A. So we see, we get this from where? From the opcode sheet we got it. So this is also can be easily predefined. So all the instructions will be present here. All the opcodes, okay, corresponding opcodes will be present here. So you call them as binary opcode. So usually, you know, in the format, opcode is going to take 1 byte. Okay, the size for storing an opcode, you will need 1 byte. So it's 1 byte here. Yes, so it's going to be 1 byte. Right. Next, what you have is the instruction length. Okay. So now what is the instruction length? We have studied different types of instructions, RR, RS. Yes. In that, if you remember, what have I told you? I told you RR instruction will be requiring 2 bytes. SS instruction will be requiring 6 bytes. All the other instructions are going to require 4 bytes. Yes. This is what we are going to write here. Instruction length. Okay, we are going to write what is the length of the instruction, but we are not going to write 2 bytes, 4 bytes, 6 bytes. Instead, we are going to use a code. They have given a code. Okay, here, what is the code here is, say for example, if it is a 2 byte instruction, if it's an RR instruction, it is a 2 byte instruction. So the code you have to use for a 2 byte instruction is 01. Yes, is there any example for RR instruction? Yes, AR, we saw one AR. Okay, add register 4 comma 4, so that opcode is 1A, and that is nothing, the code is nothing but 01 for that particular RR instruction. Okay, so for RR instruction it is going to be 01. For SS instruction it is going to be 11. See, MVC we saw that example, it is an SS instruction, so it is 11. For all the other instructions it is going to be 10, because they all belong to 4 bytes. All this RX, RS, SI all are going to be occupying 4 bytes only, so the code is going to be 4 bytes. Yes, so this 4 bytes here means what? It is going to be one word. 4 bytes means one word, right? If it is 2 bytes, it is known as half word. So how are they here classifying it? One half word, two half word is nothing but one full word, three half word is nothing but one and a half full word. Okay, so that's what you are saying. Just have to remember, if it is a 2 byte instruction, the code you are going to use is 01. 4 bytes instruction, the code you are going to use is 10. 6 bytes instruction, the code you are going to use is 11. Right, this is going to be the length. Then you have instruction format. This you also should know what is the instruction format, only then you can decide on how we are going to place it. So each and every instruction format we have different ways of writing it, yes or no? Then we have opcode, then register 1, register 2. Some will not have register 2, they will have address. Okay, so you have a method of writing. So every different type of instruction has different way of actually representing it. So you should know what type of instruction. Say for example, if it is an RR type of instruction, the code you will use is 000, RX 001, RS 010, KSI 011, SS 100. Right? Let us see any instruction we know. Yeah, we know one instruction which is RR type 000 here. Yes, AR. Similarly, we know MVC. It is SS type of instruction. It is 100. Okay, we also know an add instruction here which comes under RX type of instruction 001. So this is the code. You have to also remember this. Yes, so there are two ways, two codes used. One is going to determine the length of the instruction, other is going to determine the type of instruction. Totally, an MOT table will be using 6 bytes. Okay, every line is going to use 6 bytes, of which 4 bytes is for the mnemonic opcode, 1 byte is for the binary opcode, 2 bytes for the length, 3 I'm sorry 2 bits. So why 2 bits here? 101, that's why we are using code to make it simpler, right? 0110, so 2 bits enough to represent. Similarly here 3 bits are enough to represent what type of instruction it is, and there are 3 more bits which is empty, which is not used, right? Okay, so this is going to be your structure of your machine op table. Machine op table, this whole thing will be already available because all the instructions are predefined. Nothing is going to be user defined. So whole thing can be ready even before you start writing the program. Yes, it can be ready. Okay, you can just have to list all the instructions of IBM 360, their opcodes, their instruction length, and their format. Okay, that is why this table is called as a fixed table. Okay, this table is a fixed table. Understand? We'll move on to the next one. Next, this table is also known as a fixed table. This table also is known as a fixed table. Why? Because pseudo ops are also predefined. You don't have to, it's not user defined. Okay. So what is it? This table? This table is called a pseudo op table. All the pseudo ops like drop, end, start, okay, using all this pseudo ops, you're going to have the list of all the pseudo ops. Again, it is predefined. So this is also a fixed table. Okay, machine op table and pseudo op table or fixed tables, because these are predefined. It can have already, you can fill this table with all these values. It is not going to change, right? So this is what you're going to have. All the instructions are here. So how are you going to write all the instructions? You're going to write it in using 5 bytes, because the number of characters I think using will be the biggest one. USING, 5 characters are there. Each character is going to be represented using 1 byte. So you will need 5 bytes, right? 5 bytes are going to, yeah, start also as 5 bytes. This is your opcodes. Okay, what do you have here are labels. So if I find that particular opcode, what should happen? I have to transfer to some label and then execute whatever is required for that particular opcode, right? So what happens here, this pseudo op has some label. Say for example, drop pseudo op has a label p1 drop, p1 end, and so on. Okay, just have to remember there are some labels, right? So how many bytes you're using? You're going to use 3 bytes to store those labels. 3 bytes. Okay, so totally it is going to be 8 bytes. 8 bytes, 5 plus 3 bytes. Okay, this is going to be your pseudo op table. So this is also a fixed table, I told you, because this is all predefined. Yes, we will move on. Yes. Now this is table is the first table which is user defined, because symbols, variables you are going to give. So it is going to change from program to program. Okay, everything about the symbol, what is the name of the symbol, where is it stored, what is the contents, everything is going to change now. Okay, so this is not a fixed table. This is a floating table only, so it is going to change. So from now on, other 3 tables we are going to see are all floating tables, not fixed, right? Let us see what is a symbol table. Symbol table is where you store especially your say variables, your labels, all these things are going to be stored in the symbol table. Okay, so what are the information you should know in a symbol table? First of all, 8 bytes is given to you, which means your symbol cannot exceed that. So you can only have 8 characters. Each character will be using 1 byte to store, to be stored. Okay, so you can only have maximum of 8 characters. So let us see examples also. See, we will take the same example. We just saw one program, right? Same program only we will take. So what are the variables there? First one was the label, the name of the program. John is the name of the program. So JOHN 4 bytes over. Again, other 4 bytes you're saying blank, blank, blank. Okay. The next variable we had is 4, FOUR. Okay. The next variable we had is 5, FIVE. The last variable we had is temp, TEMP. Right. So the symbol, first one is what is the symbol, what is the variable, right? That is what we have here. The next attribute of this database is going to be value. Okay, so value doesn't mean the contents of that particular variable. No, it is not the contents. Value here means what is the address value, where is it stored. Okay, where is it stored, what is the address value. Okay, only thing is it is the same address value. We had addresses like say 12, 16, 20, you remember? Yes, only thing is it is converted into hexadecimal and given. Okay, so the label John, start of the program, doesn't have any address. It is going to be a sudo op only. Start as a sudo op, so always it is going to be 0000, right? Length, you have to remember that it is always 1 byte. Okay, the label which you store is always is going to be of size 1 byte. Labels 1 byte. Okay, what about these variables or symbols, what is the size of them? Depends on how you do it. In, say for example, define constant, I say one full word. If I say one full word, it is 4 bytes. If I say two full word, it is 8 bytes. Again, based on your definition, what you say in the program, the size, okay, the length of that particular variable also will be decided, right? Always remember labels 1 byte. So other symbols depending on how you declare it, that will be the size of that particular symbol, right? Yes, the last one is very very important here. What do you mean by relocation? So relocation is only 1 byte, which means there is only one character. It can either be R or A. Okay, usually it is R. 90% it is going to be R. What do you mean by R here is, R means relocatable. R means relocatable. Everything has to be relocated, all the symbols. Yes, I have to know when I'm loading it into the main memory, I should know what is the address and then add that with my relative address. Only then I will get my absolute address. It has to be relocated. Yes, it has to be relocated. All these are relocatable values. Yes, but there are some values which you don't have to relocate. Okay, one example. So there is only one such thing. Say for example, when I'm using EQU, you remember the sudo op EQU we used? Yes. So that, what is that example we used for EQU? We used base EQU 15. We used base EQU 15. What does that means? 15 will be stored inside the value base, BASE. Okay, it is a sudo op. Will there be an address or a memory location allotted for this BASE? No, it will not be. So it is going to be handled by the system only. Wherever there is BASE, it will replace it with 15. That much it knows. That's all it does, right? So it doesn't have a address. So what happens now? That is not relocatable. When you don't have the address, what is the purpose of relocating? You don't have to relocate, right? So it's going to value wherever it is BASE is there, it is going to blindly replace it with number 50. Okay, so it is not relocatable. That is absolute. Okay, that itself already is absolute. So that alone you have to write A here. Otherwise, everything else is R only. Only EQU. Okay, that symbol base. If base is a symbol, I will make an entry for that base, right? So I'll be making an entry for that base. That base alone is what? Absolute. Other things are all relocatable only. You understand? So this is what is your symbol table. So the symbol table size is going to be 14 bytes, 8 bytes for the symbol, 4 bytes for the value. Value here means the address. Length is going to be 1 byte. In 1 byte you have to give the length, and then whether it is relocatable or not is given by the last 1 byte. Okay, total is 14 bytes, right? The next one is the literal table. So literal table is same as the symbol table. There's no change here. On alone you have to just make a correction here. It has to be literal. Yeah, literal. It's going to be 8 bytes. Yes, what do you mean by literal? I told you in the first program, instead of giving FOUR, you can give it as is equal to F4. No, that is a literal. So that is what we have done here. So it's equal to whatever you have there. Those are literal. So I'm giving it. So if you remember in this John program, there are no literals. Okay, so I have taken simply some examples, randomly some examples I have taken. So this is a literal. This is a literal. F8 8000 is a literal. 8000 is the value. Okay, stored. So where, what is this value here is, these are the addresses wherever these are stored. Wherever these literals are going to be stored, that address location same as that of symbol, right? Length, again whatever you are declaring, that is going to be the length. Okay, that's going to give you the length. So whether it is 4 bytes, one full word means it is 4 bytes, and so on. Here also same thing, relocatable or absolute. Okay, everything here is going to be relocatable only, right? So though you say f5 is stored in say address location 20, now after you load it in the main memory, definitely that address is going to change, so it is relocatable. You understand? It's the same what do you say, structure of the database, no changes. 8 bytes, 4 bytes, 1 byte, 1 byte, 14 bytes in total, right? This is about your literal table. Okay, so whenever you're writing these tables, it's a very important question. Definitely, this question will be asked. So, what are the databases used in your assembler? Okay, this question is going to be asked, but you don't have to worry about writing the filling the table. Not required. Just write the structure of the table and it's enough. So, if you remember to fill up, you can fill up. Okay, otherwise don't worry about what should I remember these values, how can I remember values. Don't worry, you can write your random examples, but it is okay to just write the table also, but make sure you give the all the length, how many bytes it is using, what are the total bytes, all the columns. If you write, that is more than enough. So this question, to draw 5 tables, it can be empty, not an issue, right? So far we have discussed MOT table, POT, symbol table and literal table. The last table is called as the base table. Okay. Here is where you are going to say which is your base register, which is your base register. So all the registers will be actually will be there. Say for example, register 0 to register 15. So you are going to have all the registers, of which I am going to say which is the register I am going to use as the base register. So here, for example, if 15 is the base register, I have to say no, no, no for everything, and at 15 I will say yes, yes, and I'm going to say what is the relative address. Okay, so this is going to be the contents of the base register. Now, once it is loaded, it is going to change. Yes. So what is the structure of the table? It is going to use 4 bytes. 1 byte is going to say whether it is yes or no, which is yes. So 15 is the yes. So 15 is the base register, right? And what is the contents of that base register? For to say what is the contents, you are going to use 3 bytes. Yes, that's it. This is going to be the structure of your base table. Yes. So what did we see today? We saw how do you assemble a program, right? We took a small program and tried to find out the missing components, the addresses we were able to find and replace. So now you know that you will be able to convert that particular program into zeros and ones. You will be able to assemble it. But since it is a small program, we followed such this method. But when it is a complicated program, we cannot go in with the same method. So we have to have a standard method. The standard method is nothing but having databases, and you're going to take line by line from your program, and whichever line, wherever it appropriately it has to fit. For example, if it has symbols, it has to go to symbol table. It has literals, it has to go to literal table. If it has information about your base register, it has to go to the base register table, and so on. So once you fit in all the lines of code, then you will be able to easily convert them into zeros and ones. It's a concept, right? So let us see, next class we will be able to see how do we do that. So how, what happens during pass 1 and what happens during pass 2. Yes.